So on the screen, we have the graph of e to the x. And I've got a tangent line drawn to this. And right now it's at 0. And the slope at that point happens to be 1. So as I drag that point along the graph, it's going to measure all of the slopes and graph. And your job is to look at the new graph that gets made and see if you can figure out the equation of what the graph, the derivative of e to the x is. So here we go. We're going to drag it along. It's plotting all the slopes as we go. There we go. What do you think the derivative of e to the x is? E to the x. So if we go to our notes where we are today, what's the derivative of e to the x? It's e to the x. It's the only number that does that. So when you learned about e in grade 12, maybe you learned that it was connected to compound interest and continuous growth. As a value of y, you learned e with logarithms. Another key thing about the value of e, it's the only derivative that doesn't change.
What would the derivative of
2 to the x would be 2 to the x natural log of 2. So the natural log of 2 is a constant that comes out in front. And we can explore those a little bit, but for the IB course, we don't go into any powers other than e to the x. In the Calculus Advanced Math course, we look at all those other powers and how the derivatives are made. So the derivative of e to the x is e to the x. So it's easy and difficult at the same time. It's easy because the answer doesn't change. And it's difficult because it doesn't change. Sometimes you think you haven't done something right. And then you change something. And then you get it wrong. So it is a really easy derivative because the derivative is itself. Nothing changes. And it's a special rule. Okay, next one we're going to look at is the natural log. So here's our natural log graph. And here at 0, 1, the derivative is 1. And as we scroll along, it makes this shape. Now this is a graph that you graphed in grade 12. It is a function that you're aware of. It has two asymptotes, one at x equals 0 and one at y equals 0. What's hard about recognizing this graph is what shows up is really only half of a graph that you know. Any guesses what this equation would be? So what would the 1 over x? Y equals 1 over x. Or x to the minus 1. So again, if you go into university calculus, they won't just give you, like, here, I'm just giving you the rules and we're going to work with them. In university calculus, you would need to say, okay, why does this happen? How do we prove that this is true? How do we use the definition of the derivative to find it? How would that look? What would that be? And then work from there. So we can combine derivative rules with what we've had before. What happens when you have a number in front of something? It just stays there. It doesn't matter. So you have, what's the derivative of e to the x? It's e to the x. What's the derivative of 4e to the x? 4e to the x. If you're adding and subtracting, we can do the derivatives of each thing separately. So you can do the derivative here, you can do the derivative of x cubed, and then do the derivative of 3 natural log of x. Well, x cubed will be 3x squared, and natural log is 1 over x. That 3 in front just gets multiplied just like normal. But now we got some work to do. We have a rule for e to the x. We don't have a rule for e to the 5x. We have a rule for natural log of x. We don't have a rule yet for natural log of more than one thing. So in this situation, the way that it's written right now, it's not in a form that we can do a derivative of. So one of the things that we sometimes do is say, how can I manipulate an equation? How can I change an equation so this does look in a form that I know how to do the derivative of? What can you do with natural log e to the 5x? You can use your log law and put the 5x out in front. And then what's the natural log of e? 1. So I just stroked it out, but really it means that it's equal to 1. And 1 times 5x is just 5x. And now we're finding the derivative of 5x, which is just 5. Perfect. So all the questions we've done up till now, with finding equations of tangent lines, finding equations of normal lines, and such, we now can have those same questions with e to the x and log. Find the equation of y equals e to the x at the point 0, 1. So how did we find the equation of a tangent? Right? Well, if we want to find the equation of a tangent line, we're going to need the point and a slope. That's what you need to find an equation of a line. How do we find slopes? We find slopes through our derivative. So if we find the derivative of this equation, ooh, right? Notation's important here because nothing else has changed. The derivative of e to the x is itself. And we want to find it at the point 0, 1. So in other words, when x is 0, and we plug it into the derivative function or the gradient function, that will tell us the slope at that point. While plugging in 0 for x gives us e to the 0, which is 1. That's going to be the slope of our tangent line. Now you know the slope and you know the point. In this case, here I've used y minus y1 equals mx minus x1, the point slope form. Can you see this would be really easy to use y equals mx plus b? We know the slope is 1. What point are we going through? We're going through the y-intercept. So the slope is 1. The y-intercept is 1. It's pretty easy to write the equation y equals mx plus b in this case. But if you took y minus y1 equals mx minus x1 and move things around, it's pretty easy to get that same equation as well. The red line is the picture of our tangent. If you wanted to find the normal of the line too, you could, right? Remember, the normal is perpendicular to the tangent, so you use the same slope. Since the slope of the tangent was 1, the slope of the normal would be -1. And same thing, you could use the point slope or y equals mx plus b to find it. So what the derivatives of e to the x and natural log of x do is they provide us with two new functions that we need to know the derivative of. So far, we're able to take the derivative of any power, right? Even if it's fractional exponents. So we can take the derivatives of any radical. We can take the derivative of any 1 over or 3 over x or 3 over x cubed, anything that you could change to a power. And now we've added to that e to the x and natural log of x.